Okay, so today's slideshow should be pretty quick and pretty easy because you've done all the grunt work when we did that exploration. My perception is that most of you understand the general idea of what we're doing here. Moving forward, however, it's going to get more complicated because we're going to change some factors involved in these problems. We'll get to that later. Okay, so again, the first couple slides are going to be a review of what we've already done. Assuming I can get my clicker to work. Nope, he's broken. Okay, here we go. Let's see now. Oh, now it's working. Okay, find the region between two functions. We've done that already. Functions, curves, it's the same thing, whatever. We're going to deal with the idea of what happens when the top and the bottom of the function changes. We did that a little bit on the exploration, but we didn't go too in-depth into it. We're also going to reevaluate the idea of the integral being an accumulator. So adding up areas, you move from left to right. And today, you should be able to properly engage in a conversation. Okay? Sadly lacking with some people. Fake eye contact with the person we talk to, that kind of stuff. What's it called?
Like define it.
All right, so this should look familiar. I've got a function f of x. I've got another function g of x, and I want to find the area between those two curves. So we talked about the whole idea of taking the top and then creating a representative rectangle. I'll go through all this again. But there is some terminology here that I want to review, and that is the idea, or the term that says bounded by. Bounded by just means contained within. Okay, so when we talk about a bounded region, that bounded region has to be finite. It can't go on forever and ever. Okay, so like the inside of a polygon is bounded. Okay, a parabola is an unbounded region because it goes on forever and ever. Okay, so we talked about this already. When we find the area under the curve for f of x, we get that region below. Where's my region? Are you guys seeing a region on yours?
Yeah.
I don't have a region. Well, this will make for a great video. All right, so on yours you have that pink region that goes from the red function down to the x-axis, and that's represented by the integral. And then you have the green region below g. And then when you subtract the two, you get, yeah, good. Oh, this is a great job, Reed. Subtract the two, top minus bottom. Okay. Pink minus green. We get that fancy thing. One thing you need to know, if you read all that calculus speak up on top, you give reason about it, who cares? You need to know which one is up on top. When you're given a nice pretty picture, it's easy to find. If you're not given a nice pretty picture, you've got to figure out some clever way to determine which function is on top, because without that knowledge, it screws up the problem. And I'll show you some tips on how to do that in a second. As I mentioned, the important part here is always, when working in terms of x, going to be top minus bottom, which is why we need to know which function is on top. Otherwise, your function's upside down and everything goes to back in a handbasket. Okay. When we did the exploration, I talked about this idea of a representative rectangle. For something simple like this, you're not necessarily going to need a representative rectangle, but as things get crazier, you are going to need a representative rectangle to make your life easier. That rectangle has two things we care about. How tall is it, and how wide is it? The width is really easy. This is calculus, so we take that width down to really, really close to 0, which we call the, it's in here somewhere, the differential. Okay? I'm jumping the gun here. The differential, we talk about delta x, but when that delta x goes down to 0, we end up getting a value that we refer to as d of x. And so it also explains, every time we've been doing integrals, why was I hyping on this dx or dy? That dx serves two purposes. It refers to the width of the rectangle. It also lets you know which variable is the function, or sorry, which variable is, wait, what am I saying? What letter is the variable, okay? In other words, if it's a d of x, that means all the x's are variables. If it's a dy, then all the y's are variables. So the concept here should be pretty easy. If I can find the area of that light blue rectangle, then I can just use the integral to add up all those infinite number of rectangles. And remember, we will have an infinite number of rectangles because theoretically the width of that rectangle is 0. And so if you have a 0 width rectangle, it's going to take an infinite number of them to fill that space, which will give us the exact area. Okay, so we're getting into that realm again of understanding what you're doing versus just blindly solving problems because you memorize an algorithm to do that. As we continue through chapter 6, understanding what you're doing is going to prove to be a lot more helpful for you than just plugging and chugging into a formula. Even though I will give you a lot of formulas. If you understand what you're doing, the formula becomes irrelevant. Okay? So, we look at an example here. I've got two functions that you're familiar with. X squared, which is the blue one, and then the square root of x, which is the red one. And we get this little leaf-looking cat's eye thing, and we'd like to calculate the area of that region. If you want to graph it, great. You don't have to. If you get good enough at this, you can do it without graphing, but I would highly recommend at least drawing a sketch so you could keep track of what's going on. Why would you draw a sketch? Well, the one thing I want out of this is I want to know which function is on top. And I now know from looking at that picture that the square root of x is on top. Excuse me for a second. I gave you the information of the intersection point. If I didn't give you that intersection point, is it safe to assume you could all find it? Yeah? How, Ellie? Beautiful. Set the two functions equal to each other and solve. Good. Can you all find that point on your calculator? Oh, now we're a little shaky. Okay, let's practice a little bit. Bust out your calculators. Put the square root of x in y1. Put x squared in y2. I'll say that again. Put the square root of x in y1. Put x squared in y2. When you're done, hit zoom 6. So you should be looking at a graph now, probably not as pretty as mine. Yep. You'll also notice the graph by hitting zoom 6 is a train wreck. You can't see anything, so zoom in. Now, let's zoom in very carefully here. Don't just do zoom in, because that won't get us what we need. Hit the window button, and let's change the window. Make x, let's go -1 to 2, and let's make y from -1 to 2. And then graph it again. You should get a better picture. Did you just zoom in? You change it. Okay. Well, zoom in works. Zoom in won't always work, so you might want to get an idea for where you're going. Okay, so now you've got a picture of what's going on. You want to find the point of intersection. This one's ridiculously easy because we have a nice pretty answer of 1, 1. Well, but if it isn't a nice pretty answer like the AP question we just did. So if you hit, find the trace button in the top row, don't hit trace, hit second trace, go to the calculate menu, go down to number 5 for intersect. It's going to ask you 3 questions. What's function number 1? Hit enter. What's function number 2? Hit enter. And then guess. Now, why is the guess relevant? All you have to do is move the cursor closer to the point you're looking for. If you leave it too close to 0, 0, it will tell you the other point of intersection is the origin. We don't care. We care about the other point. So scroll over a little bit, doesn't have to be exact, and then hit enter, and it'll give you the point of intersection as 1, 1. Now, are you going to do that in this problem? No. You're going to do what Ali said, set the two functions equal, solve for x. You'll get your 2 answers, and we're good to go. Okay, but I need to know the point of intersection. Why do I need to know the point of intersection? Because I need to know how many rectangles in what region am I adding up. I Before I click, please write the integral now that will give you the area between those two curves. See if you can set it up correctly. Okay, we good? You got your integral set up? You're integrating from where to where? 0 to 1, very good. When you're setting up this integral, you want to ask yourself, I'm adding rectangles from where to where? My smallest rectangle is going to start all the way to the left at 0, and I'm going to continue adding an infinite number of rectangles until I get to 1. Okay, so I have my limits of integration from 0 to 1. What's the function? Let me rephrase the question. What's the integrand? Liam.
I said integrand 0 to 1, absolute value, x squared minus square root of x, absolute value dx.
Nope.
No?
No absolute values. And your function is backwards.
Oh.
Top minus bottom. Which function's on top?
Oh yeah.
Square root of x. Minus the bottom, which is? X squared. That's the height of that rectangle. The width of that rectangle is dx. So we get, there's the area of the first rectangle. That representative rectangle that I chose to draw in the middle of nowhere. Once I get that, then all I have to do is use an integral to add those things up. So I slap an integral symbol in front of it, and I go from 0 to 1, and I get that puppy. Top minus bottom, or the accumulation of all the rectangles. And those rectangles have a width of dx and a height of top minus bottom. And honestly, at this point, we don't care what the answer is. I just want you to be able to set it up. Even if this wasn't a calculator problem, it's not a difficult integral, and you can solve that on your own. Okay. But before we move on, questions before we move forward. Are we good? As they get more complicated, the other question I'm going to ask myself is, at any point in over that interval, does the top function change? Or does the bottom function change? No, in that little cat's eye thing, the red function's on the top the whole time. The blue function's on the bottom the whole time, so I'm good to go, I'm done. That problem's beautiful. Let's move on. Now, if I look at something like this, the top and the bottom change over 3 different regions. Therefore, I need 3 different integrals. R1 is going to have the blue function on top, the green function on the bottom. R2 is going to have the green function on top, the blue function on the bottom, and then for R3 it goes back to the original. Okay. Don't try to be fancy with this, just create new integrals for each region. Does that concept make sense? Yes? Okay, beautiful, thank you. All right, let's try some trig. Did I give you the picture? I did, okay, so I'll give you the picture here too. How do you find the area of that light blue shaded region? And I've already split it into 2 regions for you. So go ahead and set up your integral, fn int them, get an answer. Take it all the way to the end.
1.77990617. It's cosine x minus sine x, right? Oh, wait, no, times 2, sorry, times 2. 1.559981235.
I got it.
You've done this upside down or something.
Well, I did pi over 4 pi over 2, which is correct. So no one's wrong.
Okay, here we go. Here we go. Let's see. Using red. Here's my representative whoa, that's horrible. Here's my representative rectangle for R1. So let's do R1 first. Where am I taking integrals from? Or another way to ask it is, I'm adding up rectangles from where to where for region 1. Liam.
0 to pi over 4.
0 to pi over 4. Good start. So, what's the area of that red rectangle, Liam?
Cosine minus sine, the quantity cosine minus sine, over dx. Or times dx.
Times dx. Very good. Okay. The height of that rectangle is top minus bottom. Blue function minus green function. The width of that rectangle is dx. We're good to go. Changing colors. Daniel, what's R2? Here's my representative rectangle. Going from where to where?
Pi fourths to pi halves.
Say again, I'm sorry.
Pi fourths to pi halves.
Lovely. And my function?
Sine minus cosine, or sine x minus cosine x. Dx.
Beautiful. Well done. Okay. Plug and chug. You get an answer. Anybody have an answer, by the way? Nathan, what do you got?
0.828.
Somebody confirm.
Yes.
Beautiful. Love it.
Are you in
Okay.
agreement?
Any problems? Okay. Good. Yes.
I'm getting a negative number for the second region.
Are you in degrees mode or are you in radians mode? Should be in radians.
Maybe I am, but I thought.
It's up there. Yeah, you're in degrees.
Okay.
Were you in degrees?
Apparently.
That would do it. What do you want?
What's the point of the rectangle?
Very good. What's the point of the rectangle? Here, there is no point. It's overkill. When we get into nastier stuff, you're going to use that. That's going to become your representative rectangle. It's going to be the key to being able to solve a nastier problem. Also, it has to do with understanding the concept of I'm finding the area of that red rectangle.
Where's the
Yeah, it's a you might interpret it because maybe you had a good math teacher in geometry. You might realize that that's just a segment, not a rectangle. But it's a rectangle. Now we're in calculus. It's a rectangle with 0 width. Okay. Let's do one more and then we'll call it quits. This one's a little bit more complicated. Did I give you the picture? I did, okay. So, I'm making this a little bit easier for you because I gave you the picture. If I didn't give you the picture, you gotta work this out. You'll notice that I'm looking for the area of the bounded region. That means the enclosed area between those three functions, between the red, the blue, and the green function. I realized when I was setting up the problem, I need to do it as two different integrals because at the origin, the bottom changes. So notice in region 1, I go from red down to blue. In region 2, I go from red down to green. As soon as the top changes or the bottom changes, I need two separate integrals. Are we good? Comprende? Beautiful. Solve the problem then, please. If I'm
It'll work the same
If
size.
if I was doing it by hand, I would definitely do that as or sorry, 3 halves X. Plus 6, just so that I have downward Does that make sense? I'm going to talk while you're working. Abby just asked a great question. Would you simplify your functions? The answer is, it depends. If I'm doing an FNN, I don't care what form the function's in because I know the calculator can handle it. If I'm doing it by hand, I'm going to simplify it to minimize the number of antiderivatives I have to do. Okay, that is all carried out.
Is 2/8 the form? It looks like
It
it.
would make sense because two.
How could you check for sure?
That kind of has challenge. It's tragic.
Did you have the number? I
Wait, no, I didn't, oh, I did R1 minus.
That's right.
They're great.
It's the, yeah, 0 to 2, I think it was 6 minus 32.
I'm putting tight pants. It's like Santa.
I am. Quite
Oh, it did 12 minus
X plus
Part of
6.
We also have
I've known you since we were like 6.
Alrighty, here we go. Abby, what's R1? In other words, give me the integral that you would use to solve for the area in R1.
The simplified version or like?
Give me the big daddy.
Okay, so it's from -4 to 0, and it's x plus 6, and minus, or plus 1/2.
I'm also going to suggest, it's a little bit of overkill in this case, but be careful with parentheses. Well, I'm going to keep going. Okay. Yeah, are we good? How'd you do? Good.
And then, I simplified it to,
Oh, I don't care right now. We'll come back. Hold on. We'll come back. We'll come back.
never mind.
Anthony, what do you got for R2?
0 to 2. And then it's x plus 6 minus x cubed dx.
Wonderful. And Mae, what do you got for an answer?
I don't have an answer.
Oh, boy. We were doing so well. Anybody?
Bad.
Hey.
Are you asking for like the separate answers or the?
I want the
Okay, 22.
22 exactly?
Yeah.
Shut up. Is it really?
Yeah.
Yeah, I wrote a problem that had a nice, pretty answer. Pretty cool. I hope that's right. Well, we'll go with it. We're all done. Questions? Again, this is a building block. These are going to, hopefully, these seem like very easy problems. Walking around the room, walking around the room watching you set them up, most if not all of you seem like you know what you're doing. It's going to get worse, I hate to mention that. Now, how's it going to get worse? I'm going to give you a preview of what's coming up. We're going to take those representative rectangles, which you're not sure why I'm doing that, and we're going to turn them 90 degrees. And we're going to look at what happens when you have horizontal representative rectangles. Okay? And I'm also going to explain why you would do that. Why would you cause that kind of grief for yourself? We'll explore that idea. Okay? Then, I already talked about this before, but then eventually what we're going to do is start revolving things and making three-dimensional figures and going from an area to a volume. And there's about 5 different ways to do that, which we'll explore. Okay, so again, the representative rectangle is more of a concept now, not necessarily a needed thing, but as the problems get more difficult and more confusing, that representative rectangle would become your best friend. Okay, good? I do have your test graded for those of you that took it. I will post the scores later. You just can't have them back because a couple people still need to take that test. Okay? Beautiful. Discard. Come over here.